Okay, so we are in generalized linear models with examples in R. We're in chapter 2, and we're down on question 2.18. Okay, so all right, so we are here revisiting a data set that we saw in chapter 1 called the blocks data set. And this question kind of gives you a little bit of a synopsis about what was taking place there. But in this data set, there's a bunch of children, and they're building towers out of blocks, and those blocks might be cubical or cylindrical. And then different variables are being measured along the way. And so maybe the best way to look at what these variables are is to come down here. I've already and look at the data. So we have the individual child, the number of blocks that they used, the time it took them, which trial, they had 2 trials, the shape of the block, either cube or cylindrical, which we don't see here because we just see the first 6 rows, as well as the age of the child. Okay, so we're going to go through and answer some questions here that I won't read right now. I will just read as we come to them. But here, just make sure, just for this first part here, that we need the data, and so you'll need to install the GLM's data and load it into R. Okay, and this is how I got the data up. I'm just calling the data that's called blocks. I'm just calling it D. Okay. Okay. So the first part is is to reference us back to problem 1.9, which is in a different Colab sheet, so you should be able to find that, and then to use those plots to summarize possible relationships with time, or just possible explanatory relationships. Okay, so this is very open-ended because if you really start to, if we exclude child, and if you start to look at the combinations of possible relationships here, there's a lot of possible relationships here. So I don't really know how useful this particular exercise is, and in fact, I'm going to have something to say about the formatting of this question that I don't really like. But I've generated a plot here, and you can kind of look at this code, but we'll look at the plot. You can play with the code here, but basically I have the trial number for each child. So each child is represented by a line here. Okay. The age of the child is represented by the darkness of the line, which maybe wasn't a good choice, but you can see some very faint lines and some very dark lines representing young and old children. The shape of the block is coded as either a hollow square or a filled circle, the square being cubes and the circle being cylinders. And then the size, the size of the marker is indicative of the number of blocks being used. Okay. So now we could break this out into different 2-way relationships or 3-way relationships, and that would be fine. But I just tried to put it all in one. That way you could go through and play with the individual variables and pull out the things that you thought were important. So, okay. So now questions, or parts 2 through 4, ask us that we have systematic components of our models that look like the following here. Time regressed on either age by shape, age by trial, or age plus shape by trial. Okay, and it says, what would these different systematic components imply about the relationships? So I don't know how to say this other than the following. So if we have age by shape, okay, well, I mean, quite literally what this is saying is that the relationship is such that time can be modeled as a linear function of age, shape, and the interaction between age and shape. But that's that is just a verbatim reading or translation of that particular R formula. Okay, so I guess that's really my best answer there, right? So whenever we look at these, it's just saying that time can be modeled as a linear function of the terms to the right-hand side. So, okay. All right. Parts 5 and 6 here. So both 5 and 6 give different hypotheses, okay? And so we're supposed to test these hypotheses. All right. So the first hypothesis is that the time taken to build a tower differs between block type, or the shape of the block. Test this hypothesis with a regression model, linear regression. So here, so that's what this model is representing. So I'm just regressing time on shape, okay? Now, let me say this. One possible way to interpret this, I'm trying to take the most straightforward interpretation, but one way to interpret this is that shape is important for predicting time after controlling for other variables. Okay, I mean, you could read the question that way, but this only mentions shape, and so I'm only including shape in here. Okay, but if other variables are actually important, whatever results that we get here are not really valid in the real world, right? They're only valid if in the real world shape is the thing that is important in time without controlling for anything else. Okay, so we'll look at the output of that regression in a moment. Now, another hypothesis is instead that that age is important. Okay, that older children will take less time to build towers than younger children, but that the difference depends on type of block. Okay, so if I'm interpreting that correctly, it's saying that time can be modeled as a linear function of age, of shape, as well as the interaction between age and shape. Okay. So anyway, so that's what that model is. So let's look at these here. Let me scroll up here. Okay. So right here we have the output to the first model where it's just time on shape, and we see that given the assumptions inherent in the model, it seems that shape is important. Okay. Now we go to the, well, and then let's look at the, I plotted it as well. So this is shape, and then the time it took. So this is just a box plot of the times that the times taken under both shapes of blocks. Okay. Now this part here is the second regression. Okay, where we're using age by shape. So we have an age effect, or a term for age, a term for cylinder, and a term for the coefficients. Okay, and now this model suggests that maybe none of the individual terms are important. Okay, so let me come back to that in a second. But here's a plot of that, right? You can really see that it's kind of all over the place. But we have age, we have time. Yeah, so there doesn't seem to be really any clearly discernible pattern, but that's okay. That's why we run these regressions and don't just eyeball plots. Okay, but we're starting. So when I look at these questions juxtaposed against one another, this gets a little bit. What are we to conclude then about the importance of the shape of the blocks? Okay, are we to conclude that it's important because when it's all by itself, or in the first regression where shape is the only predictor variable, that it's important? Are we to predict that it's not important because when shape enters the regression along with something else, namely age here, it is not important? Okay, so anyway, I don't know what we're supposed to conclude. The conclusion that we reach cannot be based solely on the analysis. It has to be based on knowledge that we brought to the analysis about the relationships about age and shape, etc. Right? Because depending on which analysis we run, we can get different answers to the question of how important is shape. Okay? So I just want to flag that. All right. Okay. Now parts 7 and 8, we're supposed to come up with our own linear model. Okay. Do I think that the model is suitable and explain? And then part 8 is interpret the findings. Okay. So so just kind of piggybacking on kind of my critique of this particular question and the type of thinking I believe that it's kind of supporting, is so I'm going to come up with a model here, okay? And I'm just going to say that trial and age and shape are all important, but that they're interactions, that there is no interaction between these different terms, okay? That's what this, maybe make that a little bit nicer looking. That's what this model is implying, okay? Now, do I think that this model is suitable? Well, I don't know, because I'm not a subject matter expert in all of this. And the model that we use should really be based in subject matter knowledge, of which I have very, very little. None. No more than any, adult person might have about children and what they do with blocks, okay? So do I think that this model is suitable? I guess, but the thing that I am not going to use the thing that I'm going to use sparingly as evidence of how suitable this model is the outcome of the analysis, right? Because because the analysis is predicated on assumptions I'm making, which is the reason that I'm choosing this particular model. Okay, and if those assumptions are wrong, well then, the model doesn't tell us anything. And if the assumptions are correct, and I get low or high p-values across the board here, meaning that none of these is apparently important according to those assumptions, that does not necessarily mean that the model is not suitable. Okay, so anyway, so we do this. So in this particular set of assumptions, it says that shape is critically important. Okay, when we account for trial and age. All right, but just to continue to harp on kind of the line of reasoning that I think this question is leading us through, that I think is erroneous. So one of the factors that has not been discussed at all is number of blocks. Okay, that seems to be incredibly predictive of time. Okay, so if I add that to the regression here, well, now all of a sudden we see, well, okay, yeah, indeed, number of blocks is really, really important. And now shape is not important and age becomes important. Okay, so now this is not to defend one model against the other. It's, again, to criticize the line of reasoning I think is being facilitated by this question, right? That somehow we can determine the appropriateness of a model given the summary output of that regression, which is just not correct. Okay, so anyway, I will get off my soapbox and call that good.